Hello, everybody, and welcome. This is a story about a heavy lift drone. This is told by my perspective on it. This is in Keyshot. We're looking at an image of a mountain range taken. This is just a photo from Google Earth. It's near Gunnison State Park in Colorado. This was the original drone. I didn't put tilt rotor on it because it landed nose up and tail down. And I realized that this is not going to be able to carry people. And it's my opinion, when you make a heavy lift drone, a real heavy lift drone that anybody would care about. These jet engines are $3 million each. These are the Rolls-Royce CTS 800 helicopter turboshaft jet engine. A drone of this size will be carrying a payload that's big, a payload that's valuable, and a payload that they care about. And they're going to want human beings on board to fly with it. I think that's just simply true. And so I stopped working with this drone because I don't think that's where the money is going to go. So we will disappear it. This drone is modeled, or is in fact, the plane that is the de Havilland DHC-2. This was originally created as a cargo plane for use in unimproved runways and now the way I created this, it's just a picture of Gunnison with the plane out there in front of it, but it makes it kind of a cool image. And I thought this was a great plane to use. I have one of the stories about the heavy lift drone is, why do they feel like they have to make a new airframe? I think I know why. With the battery systems and the motors and the electrical power structure, they have really, essentially, they don't have enough power. And so they solve this by lowering the weight of the device. And the way they lower the weight of the device is to create a brand new flying structure. And my suggestion is, stay with something that works. And the real issue of a heavy lift drone is really the most central issue of a heavy lift drone is that of the heavy lift drones, in my opinion, that anybody with money is going to want to pay for, is a cargo plane that doesn't need a runway. And it needs to have people be able to carry people, which this plane does. And by the way, if both of these engines stop, this is an airplane. This could do a non-power gliding landing. And I just think that's reasonable and safe, and it already exists. And what is the point of creating a new airplane? That's not really the issue associated with drones. And so one of the questions we'll come up with, now you'll see it has 6 propellers, and they can create vertical thrust, but they are actually tilt rotor propellers, so they can also they can have themselves be tilted, and I'll get some better information on this. But they can be brought down to generate horizontal thrust and bring the plane into acquiring airspeed, so it's flying with its wing. This whole plane as a structure, takeoff weight is 6,100 pounds. That includes the plane plus 2 crew members. I've only shown one. Plus 1,000 pounds of payload, plus 600 pounds of fuel. These engines make 1,000 horsepower each, and they are powering the bent axis hydraulic pumps from Parker Hannifin. This generates enough flow to send hydraulic fluid to these hydraulic motors in these propellers. That's the basic concept. Now this is what I call a fat cord propeller. It's optimized for thrust at 0 airspeed. the simple truth of a drone is if you can't get the drone off the ground, what's the point of the rest of the drone? So these are 6 feet in diameter. There's 6 of them. The reason I chose 6 is because there's human beings on board, and if you had catastrophic loss of one propeller or one motor, you probably could do at least a reasonably controlled landing with 5. And these are a pusher propeller, and the only reason this is a pulling propeller for horizontal flight, this is a pushing propeller so that the 2 motor propeller units are located on the same structural support beam. So this is pushing the air down, this is pulling the air down, and when this does tilt rotor, it's pushing air backwards, and when this does tilt rotor, it's pulling air forward. But that's only so that they can both be connected to the same support beam. And I will address the question of, so where did the drone come from? And there was a comic strip, Calvin and Hobbes. Calvin was kind of a smart-mouthed little guy, very intelligent, full of himself. He had a stuffed toy tiger, which for him was real. It walked and talked, and he kept it with him all the time. In one of the comic strips, he was sitting, it was a lemonade stand, except Calvin wasn't selling lemonade. His sign said, "Swift kick in the butt, 50 cents. And he had a kind of a sour look on his face. And the tiger walks up and says, "How's business?" And Calvin says, "Terrible. I can't sell any at all." And the tiger, I love this phrase, the tiger says, "Well, why am I not surprised?" And Calvin says, "I don't know, I just don't understand it. Everybody I've ever met needs one, but I haven't sold any." And on the topic of the heavy lift drone, my statement is, why don't they have a heavy lift drone? Everybody wants one. They can't seem to make it. And I thought, that is just so weird. And I thought, well, maybe they don't have a heavy lift drone because it's not possible to make one. And I thought, well, I'll just do some math and see if I can see if that's true or not. And so that was the beginning of the heavy lift drone story for me anyway. All right, and we've changed the scene a little bit, and we're on again, this is in Keyshot. This is that drone. And the question is, so where did drones come from anyway? And you might say, well, they had a propeller, and they had it going around pushing air down instead of pushing it back towards the back of the plane. That's how it happened. And the answer is, that's not true. They had those propellers in 1930. Oh, well, but you see the motor on the plane turned the propeller around like this. And they had to get the motor to turn the propellers around like that. And the answer is, no, that's not true either. They had those motors. It's not hard to change how a motor spins. Well, they just put the propellers on. They didn't think of it. And my answer is, what do you mean? Well, you can have a guy, and he has this little box right here, and each of these knobs controls one of these propellers. And he takes his hands and puts it on these knobs and controls how the RPM is, and the drone flies right up on into the air. And the answer to that is, no, that's not true. Because every time they did that, it immediately crashed. What they discovered was human beings it's 6 different calculations if there's 6 propellers. And these calculations have to be done very quickly, and they have to be very correct. And the movements of the knobs have to be tiny, sometimes incremental motions, very high precision. And they all have to be turned at the same time. And why are you turning those knobs? Well, you're taking your eyes and you're looking at the drone, and when it starts doing something you didn't like, you turn these knobs around so it won't get tilted and out, not in a stable condition. And all of that is just simply wrong. Human beings can't do that. They can't do those kind of calculations, and they can't tell what the drone is doing with enough precision and fast enough. What actually allowed drones to occur is they made a digital tilt sensor that very, very accurately measures tilt and gives a result with what is called a high refresh rate. It gives an output every millisecond. And that can be sent to the person, but then the person has to calculate what to do with the motors, and they discovered that human beings can't do that either. And what actually allowed for a drone was someone said, look, let's take the output of the tilt meter and send it to a central processing unit and let the central processing unit decide what it wants to do about it. And the central processing unit then tells the propellers what to do. And they all crashed until someone said, we're not changing the RPM of the propellers fast enough. We need something that really can alter the RPM of the propeller quickly. And electric motors can do that. In addition to which, the central processing unit makes very low voltage digital outputs, but that can be sent to an integrated circuit power controller where a large amount of electric power is created and is available. And this controller of the electric power receives instructions from the central processing unit, and it tells each of these motors what to do. And that loop goes around where there's one loop like this every millisecond or every tenth of a millisecond. Much, much faster than what human beings can do. And this is where drones came from. When they took the human being out of the loop, the drones began to fly. To which they said, no, that's just not right, because I'm sitting here in this chair and I'm telling the drone what to do. And the answer is, no, you're not. You're telling the central processing unit what you would like for the drone to do. And the central processing unit replies silently, okay, thank you. When I get to it, I'll change the drone around to do what you're asking. But you are not controlling the drone. The central processing unit is, because you can't make the calculations for these propellers fast enough. And you can't understand the tilt sensor output fast enough. And it turns out that the thing that can do that is an electric motor. And because of that, since it's worked and they had drones and people wanted to buy them, what that got converted into is the motors have to be electric. And my reply to that is, it isn't that the motors have to be electric. What it is that the motors have to be digitally controllable with no real substantial human input. And the motors need to be able to change the thrust of the propellers fast enough to modulate the lift to compensate the drone, so when it begins to tilt into an unstable condition, the thrust of the motors can be altered and bring it back to stable. And what is fundamentally important for a very small drone, these are very small propellers that are spinning really fast, and these little small motors can change their RPM very fast. But what happens is, if this weighs 6,100 pounds, each of these 6 propellers needs to be creating 1,016 pounds of vertical thrust. That's a big motor. That's 233 horsepower. Electrically, that's 170,000 watts. That means for 6 of them, you need 1.2 megawatts of power generation capability and an electrical system that can manage 1.2 million watts and an electric motor that can change up and down its RPM rate well enough to stabilize a 6,100 pound drone. And those electric motors, maybe they exist. Now, one of the things that's interesting is in terms of how fast do you have to change the RPM. As the drone gets bigger, from an inertia viewpoint, if it starts to tilt, it's going to tilt more slowly, the rate of tilt, which means the amount by which you have to change the propeller RPM and the speed with which you change the propeller RPM begins to become spaced out. So if you were changing RPM of a 6-foot propeller, this is a 14 or 17 inch cord. If you change that as fast as you're changing a 6-inch propeller, the propeller would be torn to pieces, and so would the motor. But it turns out with a really big drone, you don't have to change everything that fast. If it starts to tilt, it's going to tilt slowly, which gives you time to change these RPM values slowly. And when I started doing this, electric motors of this power range, they didn't even exist. And I thought, well, that's really interesting. But there is a motor that exists. The bent axis hydraulic motors exist, and they've been around for 50, 60 years. This is Parker Hannifin, and what you do is you just go to the Parker Hannifin website and you find a Parker Hannifin bent axis hydraulic motor, and you find a motor that has the power output that you need, and you directly couple the motor to the propeller. These motors are made with roller ball bearings in them. They're already used for this kind of work. And you just pick the motor you want, and you have the power. And this, I think, is what allows you to make this drone, to which someone will say, yeah, but hey there, Dr. Gray, why don't you just don't make a drone like this? That's pretty big. And I'll get into that in my next conversation. So we have the discussion of where did the specifications come from for this drone? I think it should be a military heavy lift drone because it will help the soldiers not to be injured. It will help evacuation, medical flight. It can carry supplies and ammunition. Remember, this is a heavy-duty cargo plane that doesn't need a runway. I think the military would like that. I think the military has money. They don't have to generate a profit. They don't have to sell anything to anybody. All they want to do is own something that helps them. It trickles over into the commercial world where the commercial people remove expense parts that aren't needed and try to get a use where they can generate income. But the military doesn't have to do that. And in addition to which, you're helping people that need help. So with respect to the military, I think there's two ways that you can bring something into the military. One way, now we just ran into the wall, so I'll move up a little bit. One way to bring stuff into the military is for you to go and tell the military what they want. And then they agree with you and buy it. But I think another way that makes more sense to me is to go to the military and say, well, what do you want this drone to do? And that, I think, begins to create. Now, I have changed the opacity of some of this structure so you can see inside of it. This is the DHC2. The size of it going from one side to the other side is 5 feet. And going from the floor to the ceiling is 6 feet. And the amount of space behind the pilot, it does begin to shrink as you get towards the back here. But this distance from here to here is 17 feet. So with respect to the military, what do they want? My opinion is payload is important. So let's give it 1,000 pounds. If it can't lift 1,000 pounds, they don't want it. What is the other thing? They want range. They don't want it to go up in the air and have to land in the next 20 minutes. So what does that mean? It means something that the drone people are slowly realizing, which is the whole point of a heavy lift drone is fixed wing flying. At 6,100 pounds, it takes 1,600 horsepower for this drone to go straight up. Once it's flying, from a drag and resistance viewpoint, it only takes 300 horsepower to have it fly at 125 miles an hour. 125 miles an hour, the stall speed is 60 miles per hour. At 125 miles per hour, the fuel use is 136 pounds per hour. So if you have 2 crew members and the drone and 1,000 pounds of payload and 600 pounds of fuel, these 2 jet engines can get it up in the air. It can go from 0 to 500 feet of altitude in 30 seconds using 20 pounds of fuel. But then you switch to fixed wing as soon as you can by doing tilt rotor. You can see that these little hydraulic cylinders, if they extend, that this thing will rotate down, and you bring the drone over to fixed wing flying as soon as is reasonable. Once it's going above 60 miles per hour, you don't need vertical lift equal to the weight of the drone. The wings will give it to you. So at 125 miles an hour, using 136 pounds of fuel per hour, starting out with 600 pounds of fuel, and putting in a safety margin, this drone has a 300-mile range with 1,000 pounds of of payload. And it doesn't need a runway. It just goes up in the air and flies off. So to me, that was what we should be offering to the military. Now, I wanted to show, these are Heskey sandbags, and these are little trusses. Out in Alaska, these trusses are used to make bridges for side-by-side and four-wheel drive vehicles, but you can shrink it where one end is wider than the other end, and you can put these on top of the Hesco bags, and you have yourself a little hangar that's protected against small arms fire and some mortars. And that's what that's all about. But they would let their little drone tractor pull the drone out of here to there, and then the drone just goes straight up in the air and starts doing fixed wing flying as soon as it can. And it flies soldiers to medical care, or it goes and gets the wounded, or it delivers more ammunition or more food or more fuel or whatever it's delivering. It doesn't need a runway. And so that's why I created this drone, is because I decided, let's give the military what they want instead of creating a drone that can pick up a loaf of bread and carry it 2 miles, because who cares? And on the battery issue, once you get a battery that can move 6,100 pounds, you've wiped out your payload. The payload will be the battery. And so that's why I went to a fuel system. That's the drone I'm talking about. And I know you're going to say, well, Dr. Gray, you are dreaming. There's no way that you can make this drone that you're talking about. But I'm not so sure about that. I have a website. I asked some of the mannequins if they would walk in this poster, and I'll show you. I do have a YouTube channel named Patrick Gray. I invite you to subscribe. I think you will like it. I do have a website. The name of my website is pistonrobot.com. And on the topic of the heavy lift drone, you go to the menu, and then you go to discussions not about a piston robot, and then you go to heavy lift drone autonomy discussions. I have 2 heavy lift drone pages. This is the most recent page. The other page, I think, is named heavy lift drone. It's all of my work going back for a while on the drone topic. And I do, anytime we're talking about physically real structures, particularly something like a flying device, any physically real object has the potential that it could hurt somebody or damage things. if you are managing a physically real object, it is my advice that you manage it in a manner that is legally allowed and reasonable and safe. And if you cannot manage it in that way, it is my advice, do not create it as a physically real item. Just put drones and jets and anything, really. And the other thing is, I always like to see what Microsoft has for us. This is area wilderness. I think maybe Minnesota. I don't know where this is. But it sort of reminds me of Alaska. And I think this YouTube video could be an investor presentation. Not by me, really, because I'm nobody. But if you know investors, you can show this video to anybody you want to. It's okay with me. But this sort of reminds me of Alaska. And the interesting thing about this drone is it's a cargo plane that doesn't need a runway, which means if there was a heavy snowfall and the roads were all messed up, you could put fuel oil in this plane, diesel, and fly it out to outlying small neighborhoods. In Alaska, diesel fuel is available in Anchorage at $3 a gallon. And it's for sale in these outlying small communities for $15 to $20 a gallon. So you could, A, make a profit, and B, help these communities, if they're snowed in, to have enough energy not to be in trouble. In addition, you could have a air ambulance system in Alaska. Well, that's not a military use for this, but the numbers seem clear to me. Anyway, thank you, Bing. And we'll put this back to here. Now, on the website, I include some math analysis to show that it seems by math that this drone is completely feasible. So let's look at the website. And while we're getting to the website, I just wanted to show you, this is a super close-up view of the way that I handle the issue of tilt rotor. These are nothing more than hydraulic cylinders. I put 2 in there for redundancy. And this is a frame that holds the motor, and the motor is connected to the propeller. So when these are fully extended, you're configured for horizontal thrust or fixed wing flying. And if they're a little bit extended, then you have a component of vertical thrust and a component of horizontal thrust. And if they're fully retracted, you have purely vertical thrust. And the thing about this approach to tilt rotor, and let's see, we can show one other thing here. This is a kind of expanded view of the plane, where here it's set to go straight up, and here it's giving itself a little bit of horizontal thrust and a little bit of vertical thrust, and here it's completely horizontal. This plane needs 1,600 horsepower to go straight up, but it has available 2,000 horsepower. So it can tilt these rotors a little bit and put 100 or 200, 300 horsepower into horizontal thrust and bring itself up to an airspeed where the lift is from the wing is greater than the weight of the plane, or equal to the weight of the plane, so that a lot of the electrical motor systems have conversations about problems they're having with transition. I think it's because they don't have any excess power, and they're trying to transition with some power for vertical and some power for horizontal, and if they do anything wrong, they're in trouble. But this has so much power that if anything starts happening in terms of the transition, say you only have an airspeed of 30 miles an hour, it's got enough vertical thrust to just keep itself in the air. And I think that's a real advantage. And I did want to look at the website, so we'll go over here and bring it in. This is Piston Robot. discussions about a piston, discussions not about a piston robot. And then you look at topics that interest me. And this is the heavy lift drone, the original. This is the drone autonomy discussions. And it's got, this is an image here that you can download. This is a math discussion, Montrose Regional Airport in Colorado, and some YouTubes that I've made. One of the issues that intrigues me is to try to make this drone so simple to fly that you don't need a fully and totally trained military pilot. And I think that is fundamental to this, because then the military can put the drones at a base and just assign someone at the base to fly it, because it has so much autonomy and so much computing power inside of it that the person just tells the drone what they want it to do and it does it, and it keeps itself from getting in trouble. That to me is a direction that this drone world needs to go in, and I have some discussions about that. This PDF shows the math. If you click on it, it's a free for download, and it shows the math demonstrating how these hydraulic motors will work. And I don't think this is a really expensive issue to establish that this will work. Personally, I think, and I'll go through, all you need is one propeller. Now, we'll take this back out of here. You can see these are what I call the fat cord propellers. There they are. And I have an entire YouTube video about this propeller. There is a company, Mechlidzik, I can't say their name. Here they are. Now they started out with the little baby drones, but they now have a 6-foot diameter carbon fiber propeller that makes 900 pounds of thrust. So they are starting to, who knows, but they're starting to work out into the big drone area. And they show some of their propeller. I've been very surprised that it is hard to get static thrust values for propellers. They're not on the internet. I don't know why. But anyway, I would get one propeller. And then the next thing I would do is get one motor. And because one thing about it with the drone at 6,100 pounds, take 6,100 and divide it by 6, it's like 1,600 or 1,400 pounds of thrust. Let's see what it really is. 1,016 pounds of thrust. And I put this into my propeller program, and this propeller that I have can do it at an RPM value that the hydraulic motors can do. So I would get one propeller and one motor, and I would see if I can get 1,016 pounds of thrust from it. Because the truth is, if you can't get the drone off the ground, you don't need to go any further. But that's not a really expensive activity. I'll show you some test equipment that I put together. And this is some test equipment that I created. This is made out of structural steel. So when this propeller spins around, it lifts this up and it pivots around this bearing and pushes down on that force meter. You could put a Chevrolet Suburban on this thing. It bolted to the floor. It's not going to break. Now you'll need to put it inside of a safety area in case you had a catastrophic disintegration of the propeller. And over here I'm showing a diesel marine grade Yanmar, or the ones that are famous, Yamaha or Caterpillar diesel engine. This weighs 22,000 pounds, but you don't need to obtain a $3 million jet engine to run these pumps. Here's the pumps. And you just run a hydraulic hose over here to this motor. And you lease this. For one propeller, you need maybe 200 horsepower. And you establish that this will give you your 1,016 pounds of thrust, static thrust. That's not this is, a machine shop could make this for you in a week. It's not very expensive. Now, the next thing that's important to understand about this drone, and this is the thing that is a little complex, and the complexity is it certainly works for electric systems, but nobody has a 6,100 pound drone, and nobody has a 6,100 pound drone with 6-foot diameter fat cord propellers being spun up by hydraulic motors. It doesn't exist. But you know, there have been flying programs for drones that spend $1 billion. 6 of these motors is not that expensive. 6 of these propellers is not that expensive. This is again made with structural steel. You can just pile sandbags on this until it weighs 6,100 pounds. And the way I've constructed it is, you can see that it has these legs on it that are inside. These are bolted to the floor. I'll see if I can get this to move. Okay, so I have turned the here are the blue supports right there. They're bolted to the floor. Okay, so you can see that they're in there and they're bolted to the floor. And then I have this test drone here. That's this. And we can move that. So that drone can go up in the air. But as it starts to go up in the air, if it goes too high up in the air, it runs into these supports. And this drone could tilt a little bit. We got this structure here. So it could tilt a little bit inside of this framework that's holding it. And the purpose of showing this is you can have this drone flying around in here a little bit. And if it decided it wanted to do something stupid and crash itself, it's not going to be able to because it can't get loose. And so you can bring up the whole thing weight to 6,100 pounds and put a 2,000 horsepower diesel engine to run these pumps. And you can establish that you have a stable hover. And you don't have a $3 million jet engine. You don't have any of that stuff. The other thing I created is it's going to be, I think, important to get some test values for this drone while it's moving through the air. And this can be done by putting these test stands on a flatbed trailer with a diesel engine, and you can get performance values for these propellers with various different air speeds. You don't have to have anything flying in the air. And you could take this and go to a mountain road and go from sea level to 14,000 feet on the road and establish the thrust of this propeller as a function of altitude without having to have anything flying around anywhere. I don't think any of that would be very expensive. Certainly not $1 billion. And so this is the test equipment. There's one other thing I thought, I wanted to just mention here. All right, and you can see this is my YouTube channel, and I have a bunch of different YouTubes. Some stuff about robots, but there's stuff about the heavy lift drone. And this one here, part 4, the heavy lift drone, page 76 mission, part 4. This discusses something that I think is pretty important. And I will, I create MP4 videos and then send them up to YouTube, and I'll go get that video and show it to you. All right, and this is my heavy lift drone, the Page 76 mission, part 4. And we got some stuff that we're discussing here. And the issue, all right, this is the issue that I'm discussing in this video, which is the question of how exactly is it that they keep the drone from getting unstable or having a tilt or not having a stable hover. And the way they do it is they alter the RPM of the different propellers. They alter all 6 of these RPMs at the same time. And this discussion is the discussion that I'm having on that topic of thrust as a function of time. And this is the amount of RPM change. It's just some math discussions. But the question that becomes an issue is, in order to understand what it is that keeps the drone stable, you have to know what is it that you want to be doing with the thrust. And then, having established that, you have to have something that can allow a hydraulic motor to do that. And these are just some issues that come up. And down in here, I'm showing that one of the interesting things about the electrical structure, electrical motor, electrical protocol, is they are changing the RPM of the electrical motor. And there's a volume of how much time it took to change the RPM versus the initial RPM value versus the magnitude of the change in RPM. And all of this is unknown information. Nobody knows what it is. And this is what I'm discussing. And in order for a hydraulic drone to be stable, you have to be able to alter the RPM of the propellers at a speed of change and an amount of change and a precision of change that keeps it in a stable hover. And the way I proposed to do that was with a mechanical hydraulic flow control valve. And so that's the next thing I want to show you. And again, these are just images taken from my Page 76 part 4 video. And this is, anyway, this is showing what the electric can do, but this is what's needed. This is what you have to be able to do with the hydraulic. All right, and this is the loop. This was a Allison 250 engine for a small drone. The bigger drone uses the Rolls-Royce CTS 800, but the pump makes fluid under pressure, and the fluid flows to this manifold. You can see that manifold can have 6 different outputs. I've split the manifold in half so you can see how it works. And this fluid comes in here, and then it goes up to the motor that's turning the propeller, and then the return comes back here and goes back to the pump. And what you have here to adjust the flow is this flow control stem that goes up and down, and as it comes down, it obstructs the flow. You'll notice that I have in here a channel so that the pressure down below is the pressure up above. So there's no net pressure forcing this to go anywhere. This is not an on-off valve. This is not a very standard hydraulic valve. This valve only exists to modulate the flow, because when you modulate the flow, you modulate the RPM. And I wanted this flow to be controlled using the ball nut, ball screw linear actuator, because they're extremely precise, extremely accurate, extremely reliable. And I have here, this is just an electric motor that is spinning these, spinning these gears, and that spins, eventually it turns. The way the principle of operation here is very different from what they traditionally do with ball nut, ball screw systems. in this system, the ball screw does not rotate. The ball nut rotates. The ball screw is held by this structure here that doesn't allow it to rotate, but this structure can go up and down. And the purpose, I think you can modulate the flow accurately enough to get stable hover, but I'm not going to be surprised if you have to move it 1 millimeter, and then the next time you move it, you need to move it 1.2 millimeters, and then you have to move it 3.04 millimeters. And the ball nut ball screw system can move things with that level of accuracy and with that level of repeatability and reliability. And I have down here again a ball nut ball screw controlling system that sets the flow. It's a flow control system and a overpressure relief valve. And an interesting thing is, say the drone is tilting to the right, so the right wing is getting closer to the ground. You can just add thrust to the right side of the drone. But if you added thrust to the right side of the drone and decreased thrust to the left side of the drone, you would have that net rotational force that would bring the drone back to a stable hover. And since you had a decrease of flow on the left side, but an increase of flow on the right side, the total amount of flow isn't changed. And this is nice for the jet engines because the jet engines don't like keep having to change their RPM value. And so this manifold strikes me as the way, and does this exist? It does not exist. But again, you can make just one of them and see if it works. This gives you precise, independently variable, reproducible, reliable, low friction, low loss control of 1,600 horsepower. And this is about maybe 2 feet by 1.5 feet, and it weighs 30 pounds. I mean, that's no big deal. And the whole point of a drone is that you have precise, ongoing, unending, continuous modulation of the RPM values of the propellers. They can do that electrically. When they did it electrically, they never looked back. And the conclusion of the drone community is it has to be electric. But I don't think it has to be electric. I think it just needs to be modulated. And this, I didn't realize this ball nut ball screw system needs to be lubricated. So I had to work on that problem. I'll show you a different one. And again, hello again, you can see this is inside SketchUp. I don't have it pushed out yet over to KeyShot, but it's a surround structure that is waterproof or oil proof. So this can have oil in it. And this is a gear pump, a little tiny gear. You know, these things can be, let's see here, window model. Sometimes, yeah, it's 39 inches. So I multiplied it times 10. A lot of times in SketchUp, if you have everything really small, SketchUp doesn't like that. But in reality, this is about 4 inches square. And this is that same ball nut. The ball nut is in here and the ball shaft is here, and this ball shaft can move up and down. And this is the servo motor that's spinning these gears. It's a little blades in here because there's some oil in here. It sprays the oil all over. And this torque comes out over here, turns this turns the ball nut, which makes these go up and down. This is connected to the manifold that's adjusting the flow to the propellers. But there's also a tap off of rotational shaft that goes down here and spins this gear pump. And what happens when When it rotates, the modulation of the RPM of the propellers is going to consist of this valve going up and down. And for the valve stem to be going up and down, this is going to be turning this way, and then it's going to be turning that way, and then it's going to be turning this way, and all of this is digitally controlled by the CPU. So when this turns around one way, it pumps fluid up here, or oil up here, to this part, and when it turns around the other way, it pumps oil up here, and this one will be go out over to here. So what happens is when it's turning one way, it lubricates the ball nut and ball shaft, and when it's turning the other way, it lubricates the gearbox connected to the servo motor. And I just haven't finished that yet, but I don't think this is a crisis. It's just I forgot that this has to be lubricated. All right, and then one thing I did want to just quickly mention, this again is my website, not about a piston robot, heavy lift drone. This one and this one I think have this same one right here. This is free. If you click on this, it puts 67 megabyte PDF onto your computer. And I have here a copy of that PDF. And what it shows is some of the math that I did about this drone. Now, this was originally set up for a slightly less heavy drone, but I realized that the drone needs to have people in it, and it has enough power to do this. All right, since this is a military discussion, I thought I would explain this image a little bit better that you're seeing in that PDF drawing. This is a building here. This is about 200 or 300 yards. Over here behind this rock wall, these are American soldiers that are being shot at. And they've scattered themselves behind this rock wall, trying not to get hit by the bullets coming from this building where the enemy forces are. They're up in the second story windows shooting at them. The American soldiers are in serious trouble. They've called the base and said, please help us, and the base has launched the drone. They're about 12 miles from the base. Their situation is grim, and so that's what this is an image showing. And this just takes you through, this is some weaponry that... All right, and so again, when we were looking at that PDF, we went relatively quickly. This is the showing that the rotor is tilted, and this is the drone itself. Remember, the drone has 4 uses. It can transport stuff, it can carry stuff somewhere, or it can go get stuff and bring it back. It can do the same with ammunition. It can do the same with human beings, including soldiers or special forces, or delivering special forces behind enemy lines, or picking them up, going to get downed servicemen whose plane has crashed behind enemy lines. How about the idea, this is a drone. You could send the drone to get someone behind enemy lines with nobody in the drone. So if the mission fails, nothing happens. But if it's a success, it goes to that person behind enemy lines, lands itself, they get in. If they're a pilot, they fly it back. If they're not a pilot, it flies itself back. What's wrong with that? So that's human being transport, medical care transport. One of the final possibility for this drone is that it has ammunition, weapons on board, and can deliver these weapons against the enemy. It has a pilot on it that's flying it, but a mission specialist that's inside of it. And this is a little flying, I called it a smart mortar. It's about 42 inches across. It's 9 inches thick. It flies at about 70 miles per hour. It does have, I have a whole series of lectures on this. It has flight control surfaces, so it can keep itself in stable flight. It also has navigation and has a plus or minus 2 feet targeting accuracy, and carries a 4-pound, it carries a warhead. The warhead has shrapnel plus incendiary. It's 4 pounds of C4, and it's a shaped charge device, very much like the Hellfire missile. The mission specialist in the back of the drone flies this thing. It can be programmed with targets, or it can. She is back here, and it has a radio link of video imagery, so she can just watch where it's going and send it. And there's 12 of them. So those guys who are behind those rocks called for help, and this drone was put up in the air with these 12 smart mortars on board. It took it about a minute to get up to flying speed, where it's not doing where it is able to do fixed wing flying. When it's doing fixed wing flying, the propellers are certified for 1,600 horsepower, but it's only using 300 horsepower when it's flying. So it has 1,300 horsepower of excess power available to put into the propellers, and there's a calculation we can do. I'll pull up the internet, and this is called a rate of climb calculator. So where is it? There it is. All right, so the excess power so it has 2,000 horsepower, but the propellers are certified, are supposed to be used maximum of 1,600. It's using 300 horsepower to just fly along. So it has 1,300 horsepower of excess power. The weight, kilopounds, it weighs 6.1 kilopounds. 1 kilopound. And we want the rate of climb in feet per minute. So 1,300 horsepower extra, 6.1 pounds of weight, 6.1 thousand pounds of weight, and the rate of climb per minute, we'll calculate it, is 7,000 feet per minute. So the drone, after it takes off, we can get to 18,000 feet of altitude in basically 2.5 minutes. Now it's burning 20 pounds of fuel every 30 seconds. So it's 40 pounds of fuel per minute. So it takes 80 to 100 pounds of fuel for it to get to 18,000 feet. So remember that. Now it's going at 125 miles per hour. It was 12 miles from the place where these soldiers are in trouble. It's now been 4 minutes, so it's 8 miles away. It's 3 miles high. These smart mortars have a gliding ratio of 4-to-1, so they have a range of 12 miles. If this thing is 3 miles in the air, this is 3 miles in the air. At 70 miles per hour, they will travel that 6 miles in 6 minutes. They're a gliding munition. They don't make any noise. In order to see them, the enemy soldiers would have to see something 6,000 feet in the air that's this big. They're not going to see it unless they have binoculars and look right at it. And it's traveling at 70 miles per hour and will turn, and the mission specialist will guide it into that building, and that building will disappear. So the enemy soldiers were on the second floor shooting their weapons, and then they don't exist anymore, and the building doesn't exist anymore. And now I don't have enough military training to say, well, that's how that would work. I just don't know. The drone's been in the air for like 14 minutes. And it may hang around a little bit to be sure everybody's okay, and then fly back to the base and land and refuel and add more of these if needed, and remain itself on standby for the next mission. If the enemy forces leadership was watching from a distance, to them it would look like they had the American soldiers, trouble was afoot for the Americans, and suddenly their entire building just disappeared. And my feeling on this is, well, what is wrong with that? That sounds like a pretty nice deal. All right. All right, and this is, again, this mannequin is about 6 feet tall. And so this lady or this person, if they were the mission specialist, this weighs about 40 pounds. It's 42 inches. They pick it up in the drone, and they put it in the launch area, and then they open the doors, and it falls away from the drone. And these are some fans inside of it to give it a powered ability to adjust its flying. It also has flight control surfaces. And I called this the Page 76 mission because these pilots and mission specialists out at these outlying bases that are doing this have a air combat operations manual prepared for them for these drones and these weapons, prepared by the Army with help from the Air Force, going over, how to run the drones, how to maintain them, how to troubleshoot them, and various different combat scenarios. And this combat scenario here, where they've got a building that they have to work on because it houses enemy forces that are directing enemy fire against American soldiers, that is covered on page 76 of this manual. So they call this the page 76 scenario. And you can see when they're inside the hangar area of this air combat operations capability, and they're doing their training. They're not flying and they're not maintaining, but they're training. Part of their training is that, there's a server that comes with this that goes over the training, and it goes through maintenance and training and troubleshooting and flying protocols, and the ground crew and the flying people and the mission specialist. But one of the other things it does is it will pull up combat scenarios, and they will train with that scenario. And so they've done, and over here, not only does the pilot go inside this thing and have these screens to look at, but the mission specialist goes in there too. And the mission specialist has a board close to this one so that she or he can keep up with what the plane is doing, but they can also keep up with what their weapons are doing. So they can transfer this screen to monitor this weapon. And so this is the page 76 scenario. And again, I don't have enough military, it could be with the current way the war is going, a large plane at 18,000 feet flying 125 miles per hour, it might be that's such a target that this isn't feasible anymore. I just don't know, but it might not be. I mean, it's only going to be in the air for 14 or 15 minutes. And you could have another drone that flies with it that has electronic countermeasures. But I just thought I would mention this because this is a military topic that I thought could be put onto the drone if you wanted the drone to deliver weapons. I thought the drone from a military viewpoint would have 4 functions. It can move stuff, move materials, move food, move fuel. It could move weapons, ammunition. It could serve as human being transport, including medical transport, to or from. The last thing is you could put weapons on it and launch the weapons from the drone. The only propellers I could find that had the static thrust emphasis that this drone will have are the propellers for airboats. I was very surprised. See, these are kind of fat cord propellers. I was very surprised. There is not very much information where people give you the thrust output of their propellers, particularly at the 1,000 pound thrust level, particularly for static thrust. This is my propeller calculations. This is how much it weighs. You have some weight that you add to it so it has the VTOL capability, and you have some weight that you take away from it because it doesn't have that big engine on it anymore. Again, this was a little 250 engine for a smaller drone. This is the CTS 800. And this is where you work through what do the pumps have to deliver, and this is what do the motors need. And this allows you to do calculations. They give, for the engines, it's pounds of fuel per hour per horsepower. And so that lets you work this all out. That's the information sheet from the de Havilland. And this is me going over how you transition from one to the other and what is the math involved in that. Anyway, these are all, it's all available to you and it's all written down so you can just read it. And the math, to me, seems to indicate any project I've ever done inside my head worked great. So the math supports it, but I would absolutely want to do real testing with real propellers and real motors. But at least the numbers don't say this is clearly impossible. The numbers say this ought to work. So I just wanted you to see that PDF. All right. I did want to mention this is again in Keyshot. It's Forward Operating Base Delhi in Afghanistan. This is 50 meters, about right there. And on the end of this operating base, I have added this hangar facility, air facility, for purposes of scale. And these are these trusses, and on top of these trusses would be sandbags. And there's a bomb that went off right here, and I'm trying to show that if the planes were inside here, they wouldn't have been hit. And I wanted to try to make an aircraft facility that doesn't have a door, because if it has a door and the door gets damaged, they can't get it open or they can't get it closed. And so they just back the planes back around this corner here where the effect of the bomb cannot get to the plane. And the wingspan is about 38 feet. And what I'm showing here is that these are the HESCO sandbags. There's enough space to get this thing out to here, and then from here it just goes straight up in the air and flies away. So that's what I wanted to show. And now I wanted to talk a little bit about autonomy for the drone. All right, and I wanted to talk about autonomy for a minute. This is in SketchUp. So this is a control panel setup for the drone. This is out on a desk, but it's the same control panel that would be inside the real drone. And the soldiers could sit at this desk and do training. And they actually would create, you see this has little wheels on it. So they could swing this door open and go in here. And what this is all around the person are just regular old LED screens. And so it's a kind of a poor man's simulation where he could sort of be looking out the windows, or she, and they are learning on this control panel. And this has to do with autonomy and making this drone feasible. And I'm going to take, so this is how they would do it. And I'm going to take this control panel and pull it over into Keyshot. So I want to deal with the issue of adding a new air capability to the military and the drones. Remember that the human beings are not flying the drones. Human beings can't fly the drones. If you give them full control of the drone, they will crash it. The drones are flying the drone. And I would like to expand that central processing capability and algorithms so that the drone keeps itself from getting in trouble. That, as you saw with what I showed you in SketchUp of the training area, what would happen is, the way I see this is, at the base, they would take a senior enlisted man, intelligent, motivated, who cares and is interested and wants to do this, and say, congratulations, you are now a member of our air combat capability and you will be one of our pilots. And he will sit at this control panel and learn by sitting there. This is a part of it this is exactly what's inside the drone. Here is a board that's always there. Over here, what is exactly displayed on these boards depends upon what he chooses for it to display. So it can display navigation or weapons or warnings or more detailed information about the motor or something that's wrong with the drone that it's trying to fix. These are LED screens, and once he chooses what he wants this to display, these will be populated with letters and words. The way the drone will work, in a normal airplane, you have a joystick and you fly it. And you can use the autopilot if you feel like it. The drone is a flip of that. You can use the joystick if you want to, but you don't have to. And the way this works for the pilot is he will get in the drone and he'll get the motors going. These are momentary toggle switches, so whenever you move it, it has an effect, and when you let go of it, it comes back to the neutral position. And the advantage of that is the central processing unit can reset everything if it needs to. None of these switches will be locked in a position that it can't fix. And so he holds this up and gets the engine started and gets the other engine started, and then he moves the engine from idle to the run position, and it's ready to fly. And if he's ready for flying, here's his radio setup, including ADS-B, and he can listen to 3, but one of these is the one that he can transmit on, identify friend or foe, on intercom. He has a mission specialist in the back, and he can talk to that person if he wants to. This shows him the status of his rotors and whether they are configured tilt rotor for vertical thrust or horizontal thrust. And now I created a phrase I call drone flying. Drone flying is when the drone is staying up in the air because it has vertical thrust from the propellers equal to its weight. That is drone flying. Fixed wing flying is where the drone is held up in the air because it has lift from the wings because of the airspeed of the drone. And he starts out with fixed wing flying in the off condition and with the joystick in the off condition. And he's just sitting there and the motors are running. And when he turns the altitude button, here's what it is to be reading above the ground, 0, turns it to 40. The drone will just go straight up in the air until it's 40 feet in the air, and it will just be sitting there using 1,600 horsepower, burning up a lot of fuel. He then turns his heading to whatever he wants and then adds airspeed, and he's now moving along the ground in drone flying. That's how that works. Now, I think they will very quickly learn and realize they need to get out of VTOL drone flying as soon as they can. That's reasonable because it uses so much fuel. And so he will go over here with his hand and turn on fixed wing flying. And he'll get a message on his information screen from the CPU saying, you've asked for fixed wing flying, you're not flying fast enough, we will fix this for you. And he can acknowledge it, and it will bring the airspeed up to a safe value. His stall speed is 60, so it will bring his airspeed to 70. And if he wants more, he can turn it up. And he's now flying in fixed wing manner using 300 horsepower. This is 136 pounds of fuel per hour instead of 20 pounds of fuel in 30 seconds. Now, he can just fly. He can give himself his airspeed, his altitude, and his heading, and he's just flying along. If he wants to, he can turn on the joystick. Now, I was working on the concept of a joystick that's available and usable for fixed wing flying or drone flying. And in fixed wing flying, it's just like a regular joystick. This rolls left, this rolls right, this pitches the nose down, this pitches the nose up. This is the pedals. There are no pedals. So if he wants to yaw it to the left, he pushes on this with his thumb. And these are trim. Now, when he's in drone flying, it's a slightly different joystick. Okay, so if he pushes this to the left, the drone just goes to the left. It doesn't change its heading. It just goes to the left. If he pushes it to the right, it goes to the right. If he pushes it forward, it goes forward. He pulls back on it, it goes backwards, but it doesn't change its heading. If he wants the drone to change the heading, he pushes this green button and the heading will begin turning to the right. And it will continue turning like that at that speed. The longer he holds this button, the faster it turns, until he hits this button. When he hits that button, it will stop turning and be at the new heading. And if he wants to go back, he can make it go back the other way. If he wants to increase his altitude, he pushes this button, and the drone will start going straight up. It will remain level and continue. And when he hits this button, it will stop going up. And this makes it go down. Okay, there was one other feature of this joystick for drone flying that I wanted to cover. And we've got some buttons down here. And this, you can set the joystick up, so when you set to change heading, it allows you to have it do that. And if you don't want to do that, then you can turn it off. This knob controls the maximum feet per second that you can add to the joystick. And something that I forgot to mention, or I wanted to mention, was, all right, you're in drone flying. If you move this to the left, the drone just goes to the left. But say this is set for 20 feet per second. Then if you move this all the way to the left, it will go to the left at 20 feet per second. If you move it halfway, it will go to the left at 10 feet per second. If you move it just a little bit, like a tenth of a way, it will go to the left at 1 feet per second. And so you can crank this up to, well, 60 miles an hour is 88 feet per second. So 6 miles per hour is 8 feet per second, 8.8 feet per second. So you could crank this to 9 feet per second, and your maximum travel to the left, to the right, 2 forwards, 2 backwards would be 9 feet per second, about 6 miles per hour. But if you were doing something that required some precision, you could slow it down and set it at 2 feet per second. And then if you went over halfway, it would only travel at 1 feet per second. And like if they were doing an extraction or trying to pick somebody up or land on a boat, remembering when you're in drone flying at 6,100 pounds of weight, you're chewing up 40 pounds of fuel a minute. So you don't want to do a lot of this extensive drone flying, I don't think. But I wanted to mention those controls when you're in drone flying. All right, sorry. This is what happens when you're trying to talk and look at the screen and move the images around all at the same time. Let's try again. Okay, so you get a change of heading with this button, and once you push this button and start that change of heading, it just stays that way unless you hit this button here, which sets it to 0, which you can do with your thumb. And it occurred to me that this can run up complexity, and so another, you presumably, hopefully, when you're drone flying, you might have transferred the down-looking camera to your notification screen, but if not, you probably have it here. You can put your left hand right here, and you can have your finger sort of poised on this button. And this button has a specific function, which is, as long as you don't turn it off, if you have it on, and you have change of heading occurring, if you hit this with your finger, the change of heading activity stops. So whatever the heading is, that just stays there. The same thing about increasing and decreasing your altitude. If you hit the buttons to increase your altitude and you got it where you wanted it, with your left hand you can just push this button and it will stop changing the altitude. And the effect of this is up here on this joystick. Remember, you have the joystick on and you have the device flying in drone flying mode. You can move your thumb from here to here to here to here to here. You don't have to keep trying to get your thumb inside this ring here and push this button. This is the stop button. But this button is just a mimic, or well, this button is a mimic of that button. And that's the point of it. You can put your left hand there. You got the drone where you wanted it to be. Push this button and it stabilizes. So there you go. How hard can this be anyway? All right, now here we go on aircraft design. First of all, it's a possibility. I am trying to make this so simple by using algorithms and processing abilities of the central processing unit of the drone that you don't need a fully highly trained pilot for this to work. I absolutely have the feeling that a lot of fully trained pilots would just say, well, that is crazy. I don't know. I think this is a significant and terrible problem that you have this ability you can give to the military to have air combat operations. But you're not going to be able to give them air combat operations if you keep requiring these highly trained pilots, because they don't have them. And so I was hoping to let the central processing unit of the drone is much more sophisticated than just regular planes. And I'll do a quick little tour of this board. I wanted this board to be a board where everything that this pilot needs to do, he can do. These, they have this kind of off green color. That's because these are LED screens. And when the plane is actually flying, it will display numbers here. Now, this is a set of abilities that you have to establish when you turn, say you turn this by 90 degrees, how much of your heading does it change? So you could set it where if this is 90 degrees and you turn it over here, it's now at 180 degrees. But you could also set it where this is 90 degrees and you turn it over here and it's 100 degrees. This is your scale. Another thing is, say you're at 90 degrees and you turn yourself to 180 degrees and you want to stay at 180 degrees. Well, you can take this from active to reset you'll remain at 180 degrees. You can turn this knob back up to here and turn it back to active, and now the heading you have, 180, will be straight up. So you can reset what these things are doing. This one is just that kind of information, no matter what's going on, even if you're having in your mind an argument with your spouse, there's a few things about flying an airplane that ought to be there somewhere. Like, how much time do you have, sir or ma'am? Hello, okay? And if you're getting ready to go do something at your current condition, how many miles can you fly anyway? Right there, always available. I think some of the work of this drone will be flying in a loop, either to deliver weapons or waiting or surveillance. This allows you can enable it, and these let you create what the loop looks like, and that gives you a loop. This, if you want, when you take these down to reset, if they're not controlling the thing anymore, and the autopilot will be listed as off. So that's just another one of those things for you to have to look at. And again, these are also LED screens. So when the thing is really working, there's like a vertical line here that goes over here. That's 100% vertical thrust. So it shows you where your tilt rotor is. This controls it unless you have it set where it's on automatic, which is almost always where it's going to be, unless you really are a fully trained pilot. But this should let you look at your status and reassure yourself that everything's okay. The radio is pretty self-indicating. I mean, you just type, you click these toggles you put it on set, and you click up the values that you want. This shows you how much weight is on each of the wheels. This is a pretty standard jet engine, N1, N2. How much power is it making? How much torque is it making? The fuel flow for this engine, runtime remaining, temperatures. This is kind of engine stuff. And these are some warning lights, and if one of these pops up, this thing will start telling you what the warning is. You have a mission control specialist in the back that is launching stuff, and you are the pilot, and the simple truth is, it's your plane. So you got an intercom to talk to your mission specialist, but if something starts happening where you're like, man, I don't think we should be launching something, I don't like what's going on here, you could actually hold the launch. And these are momentary, so if you pushed it over here, this would light up. If you let go of it, this would be here, and that would stay that way unless you pushed it over there, and then that one. And they're set for momentary. And there's also little displays. Now, this is, again, your electrical. All of these would have numbers here if the thing was running. This is a setup for encoding, to make it where an encryption system, so that somebody who doesn't know the encryption is not able to get the drone flying. They can't turn it on. So anyway, I thought I'd give you a little tour. I understand there might be people saying, boy, Dr. Gray, you have no idea. Nobody cares. But I don't think so. And I'm trying to explore this concept of handing this drone to somebody. Of course they have training, and they do their simulation training, and they read the book, and they care. And if they're wrong, they get killed. So they're going to be really focused here. But what I'm trying to say is, maybe we don't have to have a totally and fully trained military pilot. That's the point. And again, this is drone flying. So he could fly along, he'd probably take off, I don't know, maybe he would use the joystick, but he doesn't have to. Take off, get it flying, switch over to fixed wing flying, get himself up to 125 miles an hour and turn on the joystick and fly it just like an airplane. When it's time to be getting near to landing, he would go over here and turn off fixed wing flying, and the message will be, well, you're going way too fast for drone flying. It will start slowing him down. He'll acknowledge that, and then if he wants to, he can turn on the joystick. And one of the options he can choose, he's got some cameras. One camera, he can look at a forward-looking camera, but he also has a directly down-looking camera, so he can look down and see where he is and what he's over. And when he's over what he wants to be over, he can go over here to his airspeed and turn it to 0, and then lower himself down with this this button here. Or if he doesn't want to mess around, he can turn the joystick off and just lower his altitude. And if something is wrong, the algorithms of the CPU flying the drone will try to solve that, and will give him updates about this. And it might say, we have a problem, we think we're going to get it fixed, we'll let you know when it's fixed. It might say, we have a problem, we think you should get out of a dangerous area and land this. Or it might say, we have a problem, we think you should stop this mission, turn around and go home. Or it might say, you need to land this immediately. And he would not have to have all of this pilot. And the reason for not requiring all this specialized pilot training is, if you have that level of training required, you're not going to have any pilots available to fly these drones. And you could send 3 or 4 of these drones out to these bases and just put people in them. And the drone is flying the drone. All you're doing as a pilot, you're just telling the drone what you want it to do. I don't see yet what is wrong with that. Why can't that be at least explored? It might show to be so dangerous that it can't be done, but I don't think so. I think the processing capabilities are now there. All right, so that is the discussion of the drone, at least the drone that I'm proposing. And I hope, hello, and I'm glad you're here, and welcome. Have a good time, enjoy. You may distribute this YouTube video to whoever you want to. And I think it would be a good civilian drone. I think it could be used for rescue. It'd be, I don't know if that DHC-2 could fly at Mount Everest. But in Mount Everest, if you get in trouble, the people who are there, they're not going to be able to get you back down. What they do is they move you off to the side of the trail and they just let you die. But, this drone could go up there. It could go up there with nobody in it and land. And you get in, and then it brings you back down. That would be interesting. Again, as I mentioned, Alaska for transport of fuel and food and emergencies. Anyway, the drone discussion. I hope you enjoy, and we'll stop at this point.